Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right. It's my great pleasure to introduce Ranjit Jala, who will talk about liquid types and using theorem proving for typed programming, predicate abstraction, and well, I'm thrilled to know what will be in the talk. Thank you.
Okay, thanks, Nikolai. Thanks for inviting me to give this talk. Let's see. I should just skip past the mom and apple pie slide since I'm at Microsoft Research. Everything runs on software. You know, this makes me extremely nervous because I tried to buy the cheapest car I could, but it turns out even that has like 64 processors inside it. So we would really like to know that the software, you know, is not entirely awful. And of course, the standard way to do it is to test it and see if it does what you want. And this is fantastic because it finds a lot of bugs. The only somewhat negative thing about testing is that when you're done testing, you don't know what else you can do. So, you know, the competing technology, or I should say the complementary technology that I'm going to talk about, is where one actually sort of opens up the box a little and tries to look at the code. And instead of trying to just test it, what you try to do is you take the program and you have somebody, ideally the programmer, write down some properties that the program should satisfy. And then you have some kind of mechanism, machinery, that looks at the program and the property, puts them all together, and tells you, yes, the program has this property. Okay? Or no, it doesn't. I can't prove that the program has this property, in which case, either it means that the system that you have is not very clever, or it means that the program actually has some bugs in it. So there's been, you know, a lot of fantastic work on technology of this kind, formal verification technology. A lot of it has actually happened right here in Microsoft Research. And I'm going to very coarsely characterize two lines of work in this area as follows. Okay, the first I'm just going to call abstract model checking, where you somehow take the program and you use some kind of abstract interpretation, data flow analysis, call it what you will, and get some sort of finite state representation of the program, and you grind through this finite state representation, possibly using a property of some kind of temporal property, for example, that locks are acquired and released in the same order. And then the checker will tell you, yes, the program either satisfies this property, or it'll say, no, it doesn't, and it'll give you some sort of explanation as to why the property fails. So examples of this school of verification technology are, well, the most famous one right from here is SLAM, of course, and a bunch of other tools that were inspired by SLAM. Then there's things based on abstract interpretation directly. ASTRI from Patrick Couzeau's group is the most famous example. Things based on SAT and predicate abstraction, such as Saturn from Stanford. Now, the great thing about this kind of technology, what I'm generally calling abstract model checking, is that it's very good at capturing path and value information. So, for example, in order to prove that some kind of locking protocol is met, often one has to know the values of certain status flags at various points. So right now the value of x is 1, or that x is positive. However, the things that these technologies tend to really not work very well at are unbounded data structures, things like lists and trees and so on and so forth. And the reason that unbounded data structures are quite toxic for model checking based approaches is because of this unboundedness. They're not finite. So somehow the analysis has to reason about some property that holds uniformly throughout the entire data structure. So this means there's some kind of universal reasoning that has to take place. There has to be some kind of quantifier instantiation, generalization, et cetera, and all of this gets quite hairy. Okay, so one has to devise various heuristics, which tend to be quite brittle. So a completely different, or so far completely different line of research has been those based on type systems. Okay, so there are, of course, type systems for functional languages and now modern languages like Java and C#, as well as tools that have been designed for existing older languages, things like lint, lackwit, sequal, and so on and so forth. And the things that type systems are really good at are reasoning about very coarse properties. Hi, Madan. For example, that x is an integer, okay, or that some for example, that y is a list of integers or a list of strings. So these are not very precise properties like y is currently the integer 12, but that y is right now some integer or some integer list. However, what type systems are not so great at is path and value information. They just throw all that away, and instead they just focus on, if you will, the shape of the data, not the actual data, not the value, but the shape of that value. And so the natural question that one would like to ask is, well, here are two kinds of approaches to formal verification which appear to have very complementary strengths and weaknesses. So can we combine them? So can we take the model checking strength of path and value information and the type system strength of being able to reason about shapes and put them together, for example, like so, to say that something is not just an integer list, but a list of integers, all of which are greater than 0. Okay? Yeah. Actually, it's not state yet. There's no state. It's not type state because state is again you're making it finite once you say type state. So, for example, with locks, you say that it exists in two states, right? So this is it's a sort of generalization of type state, if you will, and we're generalizing it with predicates. So that's one, and two is that the reason it's beyond type state is that we're going to use branch and path information as well. But you're right, it is a kind of type state. Okay, type state is very much in this direction. Okay, so where were we? So value and value greater than 0 list, and this is what's going to give us precise software verification. Okay. So how does one combine types and values? So Tom was prescient. This is really my very next slide. What you want is a somewhat fancier type system. Okay, and what we're going to do is, since we aren't interested just in finite state values of the kind that are captured by type state, but richer properties, what we're going to do is we're going to start with a functional programming language simply because they start with a rich type system. Okay, and if you want to do stuff with types, it makes sense to work with a functional language to begin with. So things like standard ML, et cetera, F#, Haskell, and so on. And what we're going to do is build a theory around a functional core, and we'll also get a verifier for a modern language. And then hopefully in future work, we'll be able to sort of move this over to more imperative settings. So what's the goal? The goal is to take a program written in a language like, say, ML, Ocaml in my case, and a property, which is going to be a safety property, and be able to answer questions like, yes, this program satisfies the property. Okay, so that's a general motivation. And now let me tell you how one goes about combining types and values. So this is a quick tutorial of how one combines types and values to get things that are kind of like type state. So the more general way that one describes this combination of types and values is what is called dependent types. Or there's another way there's another name for it, which is types that are refined with predicates over values. Okay, so type state would be an example of, you would say, this refinement would correspond to the state that you want to capture. So let's look at some examples. One we've already seen, positive integers. Okay, so the green bits are the type, and the blue parts are the refinement. Okay, it's a positive integer, very simple. How about integers between some other program variable I and another, between two program variables I and j? So here's how it's different from type state, is that you want the types to be able to refer to other program variables, or what they call depend on other program variables. So v is an integer, and now the refinement says that this value v, which describes the value that you're trying to describe, is greater than I and less than j. Okay, so this dependent type or refined type describes values that are in the range I through j. What about a list of integers between I and j? It's pretty straightforward. This describes integers between I and j, and you just slap a list in front of it. Okay, so what we're doing is just taking the type and adding little refinements here and there, and that's what's giving us this richer description of the values. Okay, so the blue parts are the refinement, and the green parts are the are the actual, just the shape. What about this? So all of these are just, these are just raw values, integers, lists of integers. What about functions? So how would you describe a function that takes a positive input I? So its precondition is that the input I must be positive, greater than 0, and the output is greater than the input. So the postcondition is that the output is greater than the input. Here's how you would write it. So I'm using this arrow notation. So this is a function type. Takes as input I, which is of positive value, and returns as output some value that's greater than I. Okay? So the part to the left of the arrow is the precondition, and the part to the right of the arrow is the postcondition. Okay, so great. So that's how one would, that's how you would capture these extra properties using types. But how might we use this for verification? So here's some program. You don't really have to pay attention to it. Believe it or not, it actually does something useful. I've forgotten what it does. But the thing to keep your eye on is that there's some division happening somewhere down there. Okay? So suppose we want to check that in this program there are no divide by 0 errors. How would you even feed the property into the system? Well, here's what you would do. You would give div, this division operator, you would say that this is the type of division. It takes as input one integer, a second integer which is not equal to 0, and returns as output some integer, which is, whatever the division is. Okay, so the key is that we're putting in this non-zero requirement into the type of the second argument. And so now, if your program can type check, if you can type check the program using this special type for the division operator, then you are guaranteed that this second argument that was passed in over here is non-zero. Okay, it doesn't matter what it was, that it's non-zero, and so there are no divide by 0 errors. Let's look at another example. Here is some program. Doesn't really matter what it does. Just look over here. So this is an array access. Okay, so A is some array, I is some index, and get AI means look up the array A at the index I. So how do we know that this index I is within bounds? That is, it's between 0 and the length of the array. Well, again, we'll just give get the appropriate type. So we'll say the type of get is that it takes some array X, some array, and it takes an index which is, it takes an index that's greater than 0 and less than the length of X. Okay, and it returns whatever, whatever is at that array. And once again, if this program type checks, then I is within bounds. Okay, so everything I've described to you has been well known. This is what is called dependent types. So what's the problem? Why am I here? Why am I giving this talk? Okay, if it's all well known. Well, here's what the problem is. So for people who've worked with things like JML, ESC, Java, Spec Sharp, etc., etc., you know that everything I've described to you is just a way of writing pre and post conditions inside the type system. So now the trouble with this approach is that, well, one has to write a lot of type annotations in order to prove that, for example, in this little function, these gets are safe. These gets happen within bounds. One has to write a whole bunch of type annotations, which are basically requires, ensures, invariant annotations, pre's, post conditions, etc., etc., loop invariants. So for example, just for this tiny little program in a system of Fenning and Z's from 98 called dependent ML, one would have to write all these green things, which are the annotations. And here, yeah.
Fenning and Z did not provide any method to infer these annotations? Okay.
No. In fact, they did not. In fact, their system was such that if you notice the way they write their dependent types, it makes it quite difficult to figure out how one would infer them. But we can talk about that later. They use a slightly different way of writing these types. So here's a snapshot of the simplex algorithm written in ML. The black bits are the code, and the green bits are the annotations. And so if you just if I just do that, what you see is about 30% of the code are these pesky annotations. And this is not fun. Much as I like my programs to be verified and so on and so forth, if a third of the code that I have to write is just hints that the verifier needs, then it's unlikely I'm going to do it. And as Benjamin Pierce says, it's not just the fact that it's type annotations. These are pretty complicated type annotations. The more interesting they get, the harder they are to write down. And so what we would like to do is to somehow combine abstract model checking and type inference to squish the annotations down to as close to 0 as possible. Okay? So what we want to do is to somehow automatically infer all these pre and post conditions and so on and so forth. As well as we'll see, this is going to let us infer properties of recursive data structures. Okay, so how can we go about inferring dependent types? It's really quite simple. Okay, there's two steps. One is that, well, we have to somehow restrict the space of types. Okay, the space is unbounded. Is it a positive integer? Is it a negative integer? Is it a prime number? Who knows, right? So the first thing we're going to do is to somehow restrict the space of possible types. And the second thing we're going to do is now once we somehow fence off the space of possible types, we'll devise an algorithm that just searches the space efficiently and therefore gives us the types we want. Okay? So the first thing, this restricting the space of types, is what I call liquid types. And the second thing, searching the space, is liquid type inference. Okay, so what are liquid types? Liquid actually is an acronym. It stands for logically qualified. Okay, so people familiar with type qualifiers will see where this comes from. So imagine that the programmer gives you a bunch of logical qualifiers. So these could be generated by a monkey for all you care. They're just some little snippets, the little fragments. For example, v greater than 0, star less than v less than star, v less than length star. What are these stars? The stars are just wildcards. Okay, they can be instantiated with any program variable. Okay, so the program, from somewhere, from thin air, you get these logical qualifiers. These are going to be the annotations in our system. And now the liquid types are types that have been refined, where each of those refinement predicates, the blue things that were used as refinement predicates, each of those is a conjunction of qualifiers. Okay, so all we're going to do is, each type that we're going to infer, the refinement predicates are just going to be which of these qualifiers can we stick into those places so that everything makes sense. That's really what inference boils down to. Okay, so you can just write down a whole bunch of qualifiers and throw it at the system, and it'll figure out what sticks. And that's going to be inference. So let's look at an example. This example I'll actually walk you through. Okay, so it's a tiny program, and I'm going to use this as a running example. How are we doing on time? So what this function does, it's called sum. It takes a parameter n, and it simply returns the sum of the integers from, let me see now, 0 through n, I think. Okay, so if n is less than or equal to 0, then just return 0. Otherwise, let s equal sum n minus 1, sum of the numbers from 0 through n minus 1, and add n to that. Okay, so it just adds up the first n numbers. So now, what's a liquid type that describes sum? Well, here's one. Using these qualifiers, I would say sum takes as input an integer. It could be an arbitrary integer, could be negative, and it returns as output a value that's greater than 0. So the greater than 0 qualifier would stick. So this is a liquid type because it's a conjunction of logical qualifiers. Okay, well, here's a slightly better liquid type. Takes as input n and returns as output a value that's greater than 0 and also greater than n. Okay, so this wildcard, I can plug n in over there. And so I get value greater than 0 and value greater than n. So both of these are valid liquid types for this sum function. Okay, great. So let's just quickly recap. The liquid type restriction, this is really what makes everything possible, is that all the refinements are liquid. They're conjunctions of logical qualifiers. Okay? And so how does this make inference possible? Well, if I give you a finite number of qualifiers, then that's a finite space of possible types. Right? For each type, only one, there's some subset of those 25 qualifiers that can go in there. And I just have to figure out what that subset is. Okay, I've restricted the space of possible types. And so now inference boils down to just searching this finite space. Okay, so let's see how inference works. Wow, really? Yeah.
Fixed point over the natural conjunction.
That's right.
So there's going to be this Houdini-style algorithm, right?
Houdini-style algorithm.
You'll start with the entire conjunction, and then you'll start whittling it down.
I'll just keep throwing stuff out.
That's Houdini.
There you go. Okay.
And predicate abstraction can be seen, at least with conjunctive things are
That's right.
are also liquid.
That's exactly what it is. Okay. Where are we? Right, liquid type inference. So Shah's put his finger on it, as he always does. You start with everything, and you keep throwing stuff out until you can't throw anything else out. Okay, that's really the essence of the algorithm. But let me now spend the next 20 minutes expanding on Shah's pithy summary. Okay, So what we're going to use is a sort of constraint-based style for inferring these, inferring the liquid types, because it turns out there's a few more wrinkles. There's a few tricks one has to do before one can apply the fixed points, and the types actually come in there. So the constraint-based style works like this. So remember how these things work. These are, not even high school math. If Alice doubles her age, she would still be 10 years younger than Bob, who was born in 1952. How old are Alice and Bob? Okay, so there's a standard trick for solving puzzles like this, which is in the first step, you introduce templates for the unknown. So we'll say Alice's age is A and Bob's age is B. Okay, in the second step, you generate constraints on these templates. So let's see what the constraints would be. If Alice doubles her age, she would still be 10 years younger than Bob. So Alice times 2 is equal to Bob minus 10. And Bob was born in 1952. So Bob's age is 2008 minus 1952. And in step 3, you solve these constraints. Okay, and you get some solution. Alice is, 23 really? Bob is 56 apparently. Okay? And so the liquid type inference algorithm follows the same, basically the same idea. This is how my mother taught me algebra. I asked her, what does x mean? And she said, x is the unknown, and you solve for x. It's a lesson I've learned well. Okay, so liquid type inference. In the first step, we introduce templates for unknowns. In the second step, we generate constraints on these templates. And in the third step, we solve these constraints. Okay? So let's see what these templates look like. So now remember that the liquid type refines the ML type. Okay? So the ML type, and this is really why everything works for data structures as well. What we have already is the shape of the value that we're trying to say something about. All we're trying to do is to slap on these extra predicates, which are the refinement predicates. So let's come back to sum. Now we already know that the ML type of sum is int arrow int. It takes an integer as an input and spits out another integer as output. And there's standard ways for doing this. People have won Turing Awards for it. It's really quite well known. So now the thing with the liquid type is, well, we don't know what these refinements are. It's an integer which satisfies some properties and spits as output another integer which satisfies some other properties. We don't know what those are. And so we'll just introduce some variables. Okay, introduce variables for unknown. So I'll say that this unknown, the input precondition, is called K1. And this unknown, the output postcondition, is called K2. Okay, and so K1 and K2 are what I call liquid type variables that stand for the unknown refinements. Okay, so far so good. Templates, sum, K1, K2, these are just variables. Now in the second step, what we're going to do is we're going to generate constraints on these templates, on K1, K2, etc., etc. And it turns out there are two kinds of constraints. The first constraints are scope constraints that tell you, well, what predicates can actually stick in here to start with? Does it make sense to even talk about a variable z, which hasn't been defined in the program? And the second constraints are value flow constraints that tell you, well, what kinds of values does this k actually describe? So let's look at the scope constraints, which simply describe which variables can actually show up in a particular type. So for example, let's revisit the template that we have for sum. Let's look at K1, which is the input refinement, the precondition. Now, there are no variables, there's no other variables in this program that are in scope at the point when this particular precondition is. Right? I mean, what am I going to say? K is greater than z, there's no z. Is it greater than 12? It can be greater than 12. But there's no other variables, right? There's no other variables in scope, and so K1 must not contain any variables. Yeah?
You also have global variables in scope?
Well, it's actually a bunch of let bindings, right? The whole program is let A in, let B in, etc., etc. So,
defined in module signatures?
Yeah, so those things can appear. Those things can appear. Okay, so there's so things that appear in module signatures, those would be in scope, and so those would appear in. So imagine that this is the only thing that's in the program, if you wish. Okay, the real constraint generation, there's an environment, and basically anything that's in the environment at that particular point in time can appear inside K. Okay, so no variables in scope, nothing in K1, and so we have a scope constraint that says there are no variables. This is the environment in which K1 is I don't know, described or evaluated. I don't know what the word is. But it basically says that there are no variables that appear in K1. Okay? Let's look at the post condition, K2. So now when I'm talking about the output of this function, Well, n, the input, is in the environment. Yeah.
Can you go back to the previous slide where you say that K1 has no variables? And if you want to assert a precondition on some, to say that n has to be non-negative as an assumption,
Yeah.
then I would assume that my liquid type has the predicate that v is greater than.
Yeah. So when I say no variables, I mean other than v. V is the special value variable, which describes the specific value that you're describing.
So what's on the left-hand side of the turnstile is not a typing environment. It's a logical context, or what?
It is in fact a typing environment.
So wouldn't you want to type v?
The way the rules are defined, v always gets pushed into the environment just before you check for.
Okay, so v is there.
V is always there.
Okay.
Yeah. Okay. In fact, not just v, it also depends on what the type of v is. Okay, so you would say there's a v that's an integer that's in the environment at the point in time when you check if k1 is defined. So if you really want the gory technical details, what happens is you take all the variables and you plug in a predicate and you say, is this predicate a Boolean valued predicate in the environment where all the other variables are defined to have these types? Okay? And so v is allowed, and v greater than 0 is a Boolean valued predicate, and so this would be allowed. Okay? Okay, very good. Let's get to k2, which is the output. Mumble. Here we go. So now here, as far as k2 goes, n is in scope because n was the input variable, right? So I want to say something about the output in terms of the input. So n is in scope, and so n can appear inside k2. So I want to say that yeah, n is fine, n is in scope when you're describing the output of this function. Mind you, s is not in scope when describing the output of this function because s is a local variable of this function that should not be exposed externally. Okay. And so I'm going to say, well, here's the scope constraint on K2, which is that K2 is basically must be typed in an environment where n is known to have the type int. Okay, so these are two very simple scoping constraints. Okay, now the more interesting kinds of constraints, the scope constraints are really sort of bureaucratic. The more interesting kinds of constraints are the value flow constraints that sort of capture, what kinds of qualifiers can I actually plug in at various places. So let's just look at a little fragment of code to see what a value flow constraint is really doing. Okay, so what these capture is the flow of values in a particular environment. So this is how we get path sensitivity. Okay, so consider this expression. If x is greater than 0, then x, else minus x. Okay, so now what is the type, what are the values that are described by this whole expression? Well, when x is greater than 0, then I'm going to pick up the value of the then expression, right? When x is greater than 0, the value of the then expression flows into the if. So the environment, under the environment where x is greater than 0, the then expression flows into the if. So I'm going to sort of draw that as this x expression flows into the whole if then else. Okay? And when x is not greater than 0, the else expression flows into the if. Okay, so this is the value flow. In this world, the else expression flows into the entire if. Okay, so this is what I want to capture with my value flow constraints. And so now we're going to write these constraints like so. I'm going to say in some environment, the value of some expression E1 flows into the value of some other expression E2. Okay? So this environment is going to contain all the branch information, all the if-then gods, as well as the assumptions made for other variables. For example, I may know that this value flow happens in an environment where x is positive and y is prime and z is odd, etc., etc. Okay? Okay, so in an environment, E1 flows into E2, which really means that in this environment, the values that E1 might evaluate to are contained inside the values that E2 evaluates to, right? That's really what value flow means. These values are a subset of those values, which in turn just means that in this environment, the type of E1 is a subtype of the type of E2. Okay, so this is really what a value flow constraint says. In some environment, some particular type is a subtype of some other type. Okay? Okay, so this is, I'm going to write this frowny or smiley, whatever it is, as the subtype relation. Yeah.
Go ahead.
So it seems like you assume that that your programs are well nested, right? So you can basically do region-based analysis instead of full-blown data flow. And that saves you, some time.
So Ranjit, I view this as the equivalent of VC generation for functional programs, right? It's like an implication here. The type is like
It's going to crunch down to an implication in just a second. Okay. It's kind of like, it is sort of like VC gen. Subtype, great. Okay, so let's go back to our beloved example and see what's going on. Okay, so this is the template that we had for sum, right? And such and such k1 arrow k2. Now let's look at the then branch. Okay, it says the then branch flows into the output. So what kind of constraint are we going to get? Well, let's just see what environment is the then branch evaluated. So here's the then branch, this 0. Okay. So what are the types that are in the environment? Well, we have a type for sum, which is this template. Okay. We have a type for n, which is the precondition, which is the input. Sorry. So n is known to have type k1. That's from the template. Okay. And further, we know that the then branch is evaluated under a guard n less than 0. Okay, if n less than 0. Okay, and so now the value of the then branch is value equals to 0. Right? This is the set of values that corresponds to the expression 0. So value equals 0. Flows into the output, and what's the output is k2. Right? So I'm going to say value equals 0 is a subtype of k2. Okay, so this is the value flow constraint from the then branch. Okay, I'm just going to simplify it. The something for various reasons is not needed. And when n is of type k1 and n is less than 0, the value equals 0 is a subtype of k2, which, as Shaz points out, is going to become an implication. Okay, so that's one constraint. Let's see, what other constraints do we get? Let's look at this place where the parameters, here's a recursive call that I'm making into sum. Okay, so I'm going to call sum n minus 1. And so here what's going to happen is that this n minus 1 value is going to flow into the input, right? So let's see, when does that happen? Oh my God, oh no, it's fine, there's an else over there. Okay, so this happens in the else branch. So when n is not less than equal to 0, the argument n minus 1 flows into the input n, which is k1. Okay, so that's the second value flow constraint. Okay, parameter flows into input. And now what we're going to do is look at this, the output of this call is going to flow into S, and that's going to flow into the output, right? So let's just look at what the type of this expression is going to be. What is the type of the output of this recursive call? Well, we know that the output of sum is of type K2, right? The output of sum is of type K2. And so the type of this expression is simply K2, which is the output, with the formal n replaced with the actual n minus 1. This is, again, if you're familiar with VC gen, this is quite standard. You just take the post condition and you substitute the formals for that function with the actuals at that particular call site. So you take the output post condition, which is unknown, by the way, at this point, K2, and you substitute the formals n with the actuals n minus 1. Okay? And so the type of this expression is K2 with n substituted with the n minus 1. Okay? And this resulting type is bound to S. It's stored inside S. And so now we're going to say that we're going to evaluate this expression. This is the value of the whole else expression, S plus n, in an environment where S is known to have the type K2 with n substituted with n minus 1. Okay, so in this environment, the value S plus n is a subtype of the output, K2. Okay, this whole else expression flows into the output. Okay, so far so good. So 3 value flow constraints, 2 scoping constraints. These are all the constraints for this function. So we've set up the constraint system, and now we're going to do what Shaz and Madhu suggested, which is a very simple fixed point algorithm that's just going to solve what K1, K2, and K3 are. Okay, so let's move to the constraint solving. So what we want to do, remember, is we just have a bunch of qualifiers, and we just want to figure out which qualifiers stick, okay, to each of these K variables. So what we want to do is we want to find a map, some solution, some satisfying assignment from the liquid variables k to sets of qualifiers that satisfies all the constraints. So the algorithm is very straightforward. It's exactly what Madhu said. Initially, you create an initial map that maps k to all the possible qualifiers, and then you just keep picking unsatisfied constraints. Pick a constraint that's unsatisfied and throw away the qualifiers that are needed to make it satisfied. And just keep repeating this until everybody's satisfied. Doesn't matter what order you pick the constraints in. Okay? This, in fact, finds a least fixed point. So let's see. What's the initial solution going to be? I imagine these are your logical qualifiers, v greater than 0, etc., etc., etc. So initially, I just map k1 to all the qualifiers, k2 to all the qualifiers. Okay? And now I'm just going to pick one of these constraints in turn and throw away qualifiers until everything is satisfied. Okay, so let's start with this one. The scope constraint, 0 less than, k1 contains no variables. So is this well formed? Yes, this contains no variables other than v. So this one is fine. Okay, so I'm going to preserve this. It's okay to leave this in. It satisfies the constraint. Okay, let's move along. V less than star. Well, there are no free variables that are allowed. The star can't be anything because no free variables are allowed. So just throw it away. Moving along. V less than star for the same reason. Nothing can be plugged in. There are no free variables. Let's move along. V less than length star. There are no free variables allowed, let alone any array variables. So you can only instantiate star here with variables that are arrays, because only then does length of A make any sense. There's no variables, no array variables, so you nuke it. Okay? So at the end of that pass, K1, this is the only qualifier left standing, 0 less than V. Very well. Let's move along to the next one, which is the scope constraint for K2. So now notice that N is in the environment. So these stars will get instantiated with something. So no free variables. So this is satisfied because, well, there's no free variable. V greater than 0 is fine. What about star less than V? Yes, I can instantiate star with N. Okay, I am allowed to use N, so I can instantiate star with N. And so I get N less than V. Similarly, over here, I get V less than N. Okay, I instantiate star with V. And now when I come here, I'm allowed N in the environment, but N is not an array. So I can't instantiate star with N. It doesn't make sense. V less than length N doesn't make sense. So I nuke it. Okay, so that's it. So at the end of, I've solved the two scoping constraints. These are the only qualifiers left standing. Great. So now let's move on and solve the flow constraints. What's the time situation? Okay, let's solve the flow constraints. So now this is where the implication comes in. Before we can, think about solving these flow constraints, let's just ask ourselves, what does it mean for a particular subtyping relation to hold? When is it that in some environment env, some type v of type t such that p1 holds is a subtype of v of type t such that p2 holds? Okay, so notice, by the way, that these two t's must be the same. The type system is going to give us that whenever we generate constraints, if the program was a valid program in just ML or the underlying type system, the two shapes of the values must be the same. You never have an integer flowing into a string. Okay, so when is this type a subtype of this one? Quite simply, when the following implication holds. Okay, if the following is a valid formula, if where env is a formula that I get, I sort of embed, I turn the type environment into a logical formula, I turn P1 into a logical formula. So env and P1 implies P2. Okay, where what I do is it's a conservative embedding. I'll tell you about I can tell you about the details of the embedding offline. But you basically take this whole thing and you turn it into a query like this. It's a query in a decidable logic. In our case, equality, uninterpreted functions, and arithmetic. Okay, so this, mind you, is just the base subtyping. There's all the fun stuff with functions and lists and so on and so forth. But in the end, it's all going to crunch down to this. Okay, just these base implication checks. So how are we now going to solve the constraints? Well, imagine that I'm trying to figure out if this constraint is satisfied, a constraint that looks like this with some k. I'm going to look at the current solution for k. It maps k to some set of qualifiers. What I'm going to do is I'm just going to ask the theorem prover, which is yikes or z3 or what have you. In this environment and p, does q hold? Okay, and if the theorem prover says it says yes, this implication holds, then I'm going to hang on to q in my solution. And if the theorem prover says no, it does not hold, I can't prove this implication, then I just throw q out. Okay, so just as before, I sort of make a pass over all the qualifiers and I keep asking, hey, does this implication hold? This one, this one, this one, this one. The ones that hold I keep, the ones that don't I chuck. Okay. So by the way, people familiar with predicate abstraction, this is in disguise a variant of Cartesian predicate abstraction, where you just look at each predicate predicates one at a time. You take their conjunction. Yeah.
So do you negate the predicates, or
you negate the predicates?
So basically, if you have b less than or equal to 0 less than or equal to b, you have b less than 0 as well.
You could imagine closing your qualifiers under such an operation, but
p would be unsatisfiable.
Oh, so you're saying it could be that p is itself unsatisfiable.
Right.
Yeah. That's entirely possible, by the way.
Start pruning at the right place. So we don't have.
Well, actually, if you think about it, just the environment itself could be unsatisfiable. Imagine you write a program where you say if x is greater than 0, if x is less than 0, something, right? In that case, the environment itself is unsatisfiable. So what that really means is that every possible qualifier flows into Q. Because it's, in some sense, Q is false. Imagine the most pathological qualifier is false. So what you're basically saying then is that this value satisfies false, i.e. this value is never evaluated. So, if false flows into some particular place, it means that that particular expression is dead code. Okay. Right. Okay. So now let's just walk through these constraints and solve them one at a time. For reasons of convenience, let's pick this one first. Okay. It really doesn't matter what order you pick them in. Right. Okay. So let's pick this one. Here's the current solution, and now we're just going to ask a bunch of queries. So here's the embedding. Right now, I know n is of type K1. K1 is values greater than 0, right? So I'm going to say, okay, n is greater than 0. That's my embedding for the environment. N is greater than 0. Moving along, this is in the branch where n is not less than 0, n not less than 0. Value equals n minus 1. Okay, so just reading those things off. And now I'm going to plug in each of those qualifiers from the current solution. So we'll start with is 0 less than v. And is it? I don't think it is. Okay, so yikes is going to say no, it's not, and so we'll just throw it out. Okay, well, can't say anything about K1. The input could very well be negative. Okay, and that's pretty much it. There's nothing else I can do. This constraint is now satisfied, right? There's no more qualifiers here. Constraint is all implications hold. So let's move on to this one with K2. Same thing. So now n K1, well, there's nothing. So there's nothing I put in, no conjunct over here. The guard is n less than 0, n less than 0. And value less than 0 implies. And now let's look at each of these in turn. Well, does it imply that value is greater than 0? Most certainly. Value equals 0 implies value is greater than 0. So yes, we hang on to that. What about value is greater than n? Or n is less than value? Well, n is less than 0. Value is equal to 0 implies value is greater than n. So this one also yes. Okay. And finally, what about values less than n? You plug it in, and this time theorem prover says absolutely not. Okay, n is negative, value is equal to 0. This doesn't make any sense. Implication doesn't hold, and so it nukes that one. Okay, so you make a pass over this constraint, and you're left with these two. And finally, let's pick the last one, which is the output one. So now let's see, how would we embed this? Well, here's what K2 is right now. 0 is less than v and n is less than v. So S is of this type. 0 is less than v and n is less than v with n replaced with n minus 1. So you substitute, you just apply the substitutions. You get 0 less than v, n minus 1 less than v. And now you plug S in for v. So you get S is greater than 0 and S is greater than n minus 1. Okay, so we're going to know that the output is positive. This is the key step. So you know that the recursive output is positive. And now let's plug in the rest of the environment. This is from the guard. N less than 0, not less than 0. And this from here, value is equal to S plus n. And now we can plug each of these in. Is value greater than 0? Well, let's see. Value is equal to S plus n. S is greater than 0. And what do we know about n? And n is greater than 0 as well, right? From here. And so this implication holds. So we hang on to that one. What about this one? Is value greater than n? Let's see. Value is equal to S plus n. And S is greater than 0. Therefore, value is greater than n. This one also holds. And so both those qualifiers are left standing, and now all the constraints are satisfied. Okay? All the constraints are satisfied, and now we had this template, we just plug the solution back in, and you get this back. Okay? And v is greater than 0, n is less than v. Okay, so that's pretty much it as far as liquid type inference goes. But that was really the most frivolous program because there was just sum, and it's a very simple integer thing. What's the point? We knew how to do all this with imperative programs. So what did the types really buy us other than a bunch of arrow notation? Well, let's see. The thing is that what types allow you to do is capture all value flow via subtyping. And so what this gives you is that things like higher order functions, these are all things that data flow analyses really suck at. When I have a function, I throw it at another function. A function takes another function as input. Polymorphism, things like generics. And finally, recursive data structures. All these things, they all just crunch down to these very simple implication constraints. Because the subtyping, the way subtyping works, is you have some very complicated type. How much time do I have? 11:20, so I have 10 more minutes. I should really cut to the chase. All these things just boil down to very simple implication constraints. So let me just show you a simple example with higher order functions. Actually, no example. I'll just show you a little cartoon with higher order functions. Yeah?
So would you be able to specify the W interest, invariant?
There's no links. This is all cheating. It's all immutable. So there's no... you can only so right now, this is an interesting question for future research. How would you actually specify things like mutable data structures?
Yeah, but even if let's say I have an array.
Yeah.
I mean, I can say all elements in the array are greater than 0 using your type.
Yeah.
But if I want to say this array is sorted, can I actually say A of I is...
We can do this for lists. With arrays, you can also specify it, but you can't... Any checking will involve reasoning about state. With the array, any reasoning about sortedness will involve, so imagine I walk over the array and I write 1, 2, 3, 4, 5, 6, 7. So I would have to reason, that I would have to reason about the fact that the array is getting updated. And right now it's not clear how to do that.
Because arrays can get updated.
Yeah.
You deal with that updating.
What's that?
You deal with that mutability in your system.
No, we don't.
You don't deal with
We don't deal with that.
I see.
What we deal with is a sort of purely functional kind of thing, where you're just working with lists and trees and you do things with those.
But Madan's question is still correct. Supposing I give you an ML program in which there is no update operation, but it uses arrays. Can you express the type that an array is sorted?
Yeah, that you can.
Okay.
That you can.
How would you do it? Do not refer to the...
All in good time. Well, actually, it remains to be seen. Let me very rapidly go through this. So what happens with higher order functions is this. If I have a function and I throw it at another function, what happens is I get a subtyping constraint that looks like this. Some function flows into some other function. And now, this is just classical type theory. What it tells you is that this subtyping holds if and only if T2 is a subtype of T1 and T1 prime is a subtype of T2 prime. Okay, so you take these very complicated types and they all just break down like this. Everything just keeps breaking down so that at the end you're just left with simple implications. Let me now, there was an example, but life is short. Let's just move to recursive data structures and see how you might specify these kind of sortedness style properties. Okay, so here is how you would write a list, a recursive. This is the simplest data structure I can think of that you can write in this sort of recursive style. An integer list is either the empty list nil or it's a cons of an integer and an integer list. Okay? So now really the way these types are written is like so. It's a mu t nil plus cons of int times t. So if you're familiar with this notation, great. If you're not, I apologize. There's but this is yeah, what can I say? Okay, mu t nil plus cons of n times c. This is a fixed point. So Madan should be, Madan and Madhu should both be all over this kind of thing. Okay, this is totally standard. No? David Dill will be appalled. Mu t nil plus cons of n times t.
Plus is just union, right?
Plus is union, exactly. Plus is just a sum, it's a union. It's these bars. And these nil and cons are just constructors. Okay, great. So now how would you specify refinements for recursive type that looks like this? So now if you look at this type, this is really a kind of sum of products, right? Each of these constructors is a product. Nil is the empty product, and cons is product of int and t, and we're taking the sum of these two. So what I'm going to do is I'm going to specify a refinement using a little matrix, where the matrix is a matrix of predicates with one predicate for each sort of point in the sum of products. So I have one vector for this guy, one vector for each sum, and inside each vector I have one predicate for each element of the product. Okay? So for example, over here P1 refines int and P2 refines t. Okay? So each head satisfies P1 and each tail satisfies P2. So far so good? And of course this is just empty because nil does nothing to refine. Okay. So let's look at some examples. Positive integer lists. Nothing, I don't say anything about the tail, but the head, each of these heads is greater than 0. Okay, nothing very exciting. Okay, so each int satisfies value greater than 0, so they're all positive. What about this? Value greater than x. True. This means each int is greater than x. So it's a list of integers, each of which is greater than some program variable x. Now here's the trick. This little this matrix, I can either apply it to the entire recursive type, or I can take this whole matrix and apply it to t, because t is also this entire recursive type, right? It's a fixed point. So I can, t actually refers to this whole thing. So now let's see what happens if I take the P1, P2 and I shove it in and I apply it to the t over there. Okay? And what I'm also going to do in this dependent style is to name the head. So imagine that each head element is called x. It's like a product, it's called x. So now each inner list, every time I construct a list, each inner list is refined by P1, P2, by this matrix with P1 and P2. Yeah?
See you could twice in the recursive type.
You could have different matrices. Exactly. Exactly. You could have different matrices at different places. And that's useful. So what do you think this is? Okay? Const of x, and the inner list is refined by this matrix. What this is saying is that this inner list is a list of values, all of which are greater than this x. And moreover, because this is under the mu, this holds everywhere inside. So what I'm saying is it's a list where every time I have an x, all the elements in the tail are less than this x. When I go inside, I have an x, everybody inside is greater than that x. Okay? So the head x is less than each tail element, and this holds for each inner list. That is to say, it's a sorted list. Okay? It's a list of increasing numbers. What about this? This is a duplicate-free list. Okay? It's a list of elements, all of which are distinct from each other. Okay? So now Nikolai anticipated the next thing, which is, well, what if the thing appears twice, which is what happens in a tree. Okay, so here's an integer tree. Either it's empty or it's a node of integer times an integer tree and an integer tree. So this is the left tree and this is the right tree. Well, here's the recursive type. Mu t, empty, or node of int times t times t. It appears twice. Left tree, right tree. So here's how you would write a binary search tree, where in every node, all the elements in the left tree are less than that node, and everybody in the right tree is greater than. I would just use two different refinement matrices. So the left tree I would refine with a matrix L, where L just said all the values are less than x. And the right tree I would refine with a thing that said all the values are greater than x. Okay, so that would give me a binary search tree. If I just tuck this inside. Yeah?
I presume you can't write disjointness in the tree.
So it's all
Left and right can't refer to each other.
Those are just disjoint by in a function. Whoa, what did I do?
Values are not disjoint. The same example which you had last time.
That's interesting.
Because I don't see how you can refer to
I
it.
need to think about it. You can't actually refer to, yeah.
The left part can't refer to the right part.
Yeah. But it could be that you could just put a not everywhere. Basically, if the left and right are disjoint throughout, then it means that everybody is disjoint. Maybe not. This is something to think about. Okay. Balanced trees. Great. Okay, so what about balanced trees? So this is with just the data, right? How would I specify a tree where at each level in the tree, the heights of the left and right tree were not too different? Okay, so say off by at most 2. I would use a balance matrix, push that off on the left. So now the balance matrix is an external matrix. And just like I named the head x, I'm going to name the left tree L and the right tree R. Okay? So here's what the balance matrix would look like. Again, this is empty. I don't care about x. I don't really care about the left tree. But the right tree is such that the height of the right tree, height of this value, minus height of the left tree is at most 2. Okay? Where height is the specially defined measure function where height of the empty tree is 0 and the height of any other tree is 1 plus the max of the left and right heights. Yeah.
You know this, you mentioned this Hindley-Milner type inference thing.
Yeah.
So they probably proved a theorem in the paper
That is.
if a program is well typed, they'll find a suitable typing for it.
Yeah.
Do you have some theorem like this?
Let's get to this question offline. It has a long answer. Yeah.
Now you introduce a new predicate, right, to all your previous predicates.
These HTs, you mean?
And what is absolute value and subtract?
Oh, so absolute value is actually shorthand. Think of this as, absolute value of x minus y is less than k is the same as x minus y less than k and y minus x is less than k. So yeah, that's not actually a new predicate, but.
But it's actually a general question, right? Because you had this algorithm and you throw things away. So what do you do when you want something else that's smaller than equal?
It all goes into the embedding. As long as Nikolai and Leo can reason about that particular operator, we can throw it all in. In fact,
if then else works.
even for example, you can have if then else, some kind of question mark expressions, things like that. So it all just goes into the embedding.
And the same with height.
Very interesting. This is again, it's a long answer. Height is actually treated as uninterpreted. But we use the structure of this measure function to basically assert. It's a bit complicated. Let me just say, height is as far as the theorem prover is concerned, height is treated as completely uninterpreted, which, by the way, is a generic cop out for anything the theorem prover can't understand. But the type system rigs it so that at appropriate places, this height definition is unrolled. So whenever you deconstruct, whenever you do a pattern match, we assert this thing in the guard, in the branch. We can talk about this offline.
When you write such a function,
yeah.
Are you guaranteed that this function will terminate?
There's a way you can rig the syntax to guarantee that it will.
But that's important, right?
It is. The measures there's a special syntax for writing these measures.
So disjoint subtrees, that seems to be fairly easy now, right? Because we can just collect the set of elements.
That's right. That's good point. Very good point, yes. In fact, you can do that. You can just have a measure that defines a set. The measure need not be an integer. It can actually be a set of elements. And then you would just say these sets are disjoint.
You can define anything as long as the theorem prover can.
Exactly.
Yes.
It's all factored into the theorem prover. Okay. So the thing is now, inference just works as before. The subtyping just blitzes everything down into implications, and you just follow these 3 steps and you get inference. So let's, this is all very well. Let's just look at some results. Yeah.
With a finite set of qualifiers, right? The moment you add this kind of new measures.
This is finite. You just have finite. You have I would have this would be a qualifier. For example, height L minus height V is less than 2. That's a qualifier.
I can have height of L. Oh,
it's not there, right? If I don't give it that qualifier, then it's not there.
There's
a finite number of templates that gets instantiated. Oh, click, where are we? Okay. So we've implemented all this stuff in a tool called Dsolve that takes in a program, a property. What are these properties? These properties are these type signatures, for example, for get and div and so on, or even just plain old assertions. And it spits out either yes, the program type checks, all is well, or no, it doesn't type check, and here's the particular operation that doesn't type check. Okay. And we've run applied it to 2 kinds of things. So one is array bounds checking. Array bounds checking in a safe language, you ask, it turns out there are actually bugs. And the second is these recursive data structures. So let's look at array bounds checking. So the first thing you do is you just, you want to check things about array bounds. Well, it turns out there's, most programs reason about array indices in a very straightforward way. So you just have 2 kinds of qualifiers. V op star, where op is, one of your favorite, less than, greater than, equals, not equals. Throw in less, strict less than as well. And v op length star, which is the array length. Okay, that's it. These 2 qualifiers. And then we threw it at a whole bunch of programs that do a variety of fancy things with arrays. Some are very frivolous. Others are more complicated. Fast Fourier transform, simplex algorithm, Gaussian elimination. And these were all benchmarks that had been previously annotated. So these are 630 odd lines, non-commented source. And what is it, a fifth or something is these annotations. While with just those 4 qualifiers, most of them are completely automatic. Tower needs one extra qualifier, fast Fourier transform needs one, and Gauss needs one. Okay, so it's dramatically more automatic. Yeah, 3 hands.
So the array bounds in simplex doesn't. So the implementation of simplex uses side effects on the arrays, but the array bounds.
Exactly. Very good. Yes. Exactly. Exactly.
So they're abstract.
Yeah. Yeah.
How many calls to the constraint solver do you have for these?
How many calls to the constraint solver? I don't have that number off the top of my head, but it's a very large number, and it's also partly why I'm here, because I was here trying to get Z3 to see if we could use Z3, and the reason we were here is we were using Yikes, and there's a little memory leak inside Yikes, as a result of which we have a budget. We can hit like 20,000 queries, after which we run out of memory. So we had to keep optimizing things so that it came to below 20,000. But there's a whole bunch. It's in the tens of thousands. Yeah, each of them is pretty fast. Yeah.
So you have no caching or anything across them?
We actually switched off caching at some point for reasons I've forgotten, to be precise. My students tell me I switched it off myself, but I've forgotten why I did it.
My question was basically Nikolai's question, but I didn't understand your answer to it.
Which was the question again?
Arrays, and they are probably mutable, right?
The arrays are mutable. So here's the thing. The types themselves, just like types in a regular language, the types themselves capture sort of non-temporal invariants. So for example, if I have a pointer, imagine I have a reference, okay, star x. My type can say this is a pointer to a positive object, positive integer, as long as all the values that pointer points to throughout the course of its life is positive. My type system cannot say that sometimes this pointer points to a negative object and at other times it points to a positive object. You see, so if I create a reference to an integer that is always positive, then my type system can tell you that. It doesn't have what Tom calls type state. It doesn't say that it's not flow sensitive in the sense that. So what that means is.
Types, right? It even will affect the VC generation. For example, if you mutate an array at offset 0 and set it to 2, and then after that you check if array at offset 0 is not equal to 2, that will fail, right?
It will fail, exactly. The thing is, for the array bounds checking, you don't need to reason about the actual array cells. The values, the contents of the actual cells.
That means your VC is not precise.
The VC is not precise. It does not handle this kind of state update.
That with a star.
Well, what it'll actually say is that the type you will infer for it is something that held both before and after the update. So it'll basically be, it'll solve out to true or something like that. Yeah?
So the cases in which you required a new qualifier, how easy was it to figure out?
It's sometimes easy and sometimes difficult. So for example, this is just some fiddly thing. These two are quite straightforward. I mean, these are like, they use double arrays or some array of arrays. So, one has to write a qualifier for those. For towers of Hanoi, this one I remember, you actually need a qualifier that says that the sum of 3 numbers, there's 3 towers, right? The sum of 3 numbers is less than, the total number of rings that you had to start with. So you would have to write a qualifier, A plus B plus V is less than C. Okay, but sometimes it is more complicated. I don't want to make this sound like it's that easy, and it gets much harder for the data structures. Yeah.
That's generally the problem, right? That you may not infer the particular type you want to, so you need to help it somehow. To best. But I think it can easily happen that even if you give an annotation with the right signature that that will hold, it's still the inference algorithm will not say that the annotation you give is actually something it can prove, right?
That's right.
What do you do in that case?
So there's 2 things. One is that there's actually 3 possibilities. One possibility is that the reason it can't prove it is because your program is wrong. And this actually has in our experience turned out to be surprisingly common. The second is that you didn't give it enough predicates. You didn't give it the right qualifiers. So there you have to figure out the thing. The third, as by the way happens with this, there's another more complicated array bounds example. It's this bit vector library. It's like 400 plus lines of code. And here it's more complicated because the object that you have to reason about is a record. There's a record where there's a len field and a bits field, and there's some funny invariant that relates these two entities. But the thing is that this particular library actually uses a bunch of fancy modular arithmetic. Okay, and our current implementation using Yikes did not know anything about modular arithmetic. So we had to throw in a bunch of these assumes. They're just, just trust me, at this point, x is less than 30. And how do I know x is less than 30? Because x was just evaluated to be 25 or to be y mod 30. So you know that something mod 30 is less than 30. So you have to throw in and assume like that constrains it. So these are the three kinds of things, three sort of possibilities. So this is a library, meaning that it's not a closed program. So we have to write down some specifications for the open functions because you can't just call it with any random input. So this is actually the bulk of the annotation, by the way, these 15 lines. And then after that, it was 6 extra qualifiers, which again were of this less than 30 type of thing, and a bunch of these modular arithmetic axioms. And we were quite surprised. We actually found a bug in this which could cause the machine to crash, which is funny because it's ML and it's a modern language and it's all dynamically checked. Only it's not. It turns out there was a particular function that uses, Ocaml exposes an unsafe, for performance reasons, it exposes an unsafe array access as well. And the interesting thing was that there was an API function called blit, which called this unsafe array access function. But check it out. The function was actually doing an explicit array bounds check. This messy if is actually an array bounds check. The only thing is that there was an off by 1. This greater than should have been a greater than equals to. And and you could actually construct a fairly involved input where very complicated.
Why would it cause the machine to crash?
Because if you call it with the appropriate inputs, this blit calls this guy, which calls the unsafe array access, which happens out of bounds, and that causes a segfault.
You mean the program will crash, not the machine will crash?
Oh yeah. I mean, the machine's not going to go up in smoke, Shaz.
No, you can't crash the job.
No, of course not.
Like
I mean, maybe you can, but I don't know how to do that. I'd be a bit surprised. Okay. What if we're totally out of time? I'm just going to. Okay, so it turns out there's a whole bunch of examples. I'm going to make this really fast. So it turns out that sorting, there's many ways you can specify sorting, right? But it turns out that particular one that I showed you is rather robust because we threw it at a whole bunch of implementation: insert sort, quick sort, merge sort. These are all with lists, and some, quick sort you can imagine it does a split and so on and so forth. This stable sort is Ocaml's implementation of sorting from its list library, which is a kind of merge sort on steroids. Everything is tail recursive, and so now the lists are sorted in increasing order. Now they're flipped around in decreasing order, and so on and so forth. But all of it, the tool can actually check that with this one needs one extra qualifier because of this decreasing. The increasing thing is there in the specification. So without any qualifiers, it just picks up the fact that these actually produce sorted lists. Similarly, there was AVL tree, red-black tree. Map is a functional, is like an associative map implementation from the Ocaml standard library. Vec is a sort of Python-style extensible arrays for Ocaml. Again, implemented as a tree. So you can it's like vectors in C++. You can add extra elements and delete elements and concatenate vectors and so on. So for these things, we could prove that the binary search tree invariant was maintained, all without any extra qualifiers. Vec, this property is a little hard to describe, so I'm not going to describe it. Similarly, the other thing, of course, it's not enough to prove that all of these produce sorted lists because the empty list is trivially sorted. You would also like to know that, actually even this is not good enough because you could just clone the elements of a list, but we have to draw a line somewhere. We also prove that the list that is produced as output is the same length as the list that was sent in as input, using again a measure much like the height measure. And this needs, tends to need a few more qualifiers. For example, if you append two lists, then the output list has length, which is the sum of the first two lists. You need a qualifier for that and things like that. For these guys, AVL tree, red-black tree, whatnot, the corresponding measure invariants, if you wish, are balance invariants. So you would like to know that the AVL tree is balanced and the red-black tree is balanced, as well as has the color property. I'm not going to go into the details of that. And that these map and vec also have the sort of, at each point, the left and right heights are balanced. And we actually have a fun story involving vec, which was written by someone you might know, Luca Di Alfaro. So it's this functional point of Python-style arrays for Ocaml. It has, find, insert, delete, etc., all implemented via balanced trees. And the balanced means that the height difference between two siblings at each point must be less than 2. And we found actually an interesting violation. Of course, when I say we found, what it really means is that the tool said, look, buddy, this does not type check. The trees are not balanced. And then you have to scratch your head and figure out, well, is it a bug in the inference engine or is it a bug in the program? And surprisingly often, it's actually a bug in the program. And in this case, we found the bug. You don't have to look at this. This is a gory screenshot. This recursive balance procedure, it's a nightmarish procedure. It's really quite long, especially long by ML standards. And it just does a whole bunch of crazy case splits. If the height of the left tree is greater than the height tree plus 2, something, all kinds of complications. And it turns out that the bug is in some specific case nested deep inside these cases. But what I found was interesting, I hadn't realized this was a possibility until this actually happened, is that you can actually use this kind of inference technology to debug the program. And you might wonder how. Well, here's how. Using Dsolve, we actually found exactly where the imbalance occurs. Okay, so it says under this particular condition is where the balance invariant gets smashed. And moreover, and here's the key, Dsolve told us how the imbalance occurred. It said that at this point, the left tree might be off the right tree by up to 4. Okay, so it would say that under such and such condition, this tree can grow much larger than the other tree. And with these two facts, it was actually quite immediate to find a test and a fix.
How did you get the second thing from your...
Because when you actually throw in these qualifiers, so the height is off by 2, right? So it turns out that at various points, so in the column actually listed a bunch of qualifiers, you need to reason that the heights are off by 1 and 3 and 4 and 5. And so while you're at it, you just throw in a bunch of, take a bucket full of qualifiers and throw them in, right? And all the stuff that's not true gets thrown away. Yes. And what you're left with, when everything else is eliminated, that which remains must be the truth. So,
also a question.
Yeah.
About your columns Q1 and Q2?
Yeah.
So what you mean by those columns is that these are the specific patterns you had to add. Otherwise, it's actually always using a whole bunch of qualifiers that it automatically infers, right?
That's right.
Oh, yeah. Okay. So the qualifiers are automatically inferred?
No, not at all. Q1 and Q2 there are some that are, like false is always used.
Sure.
But
here's the question. You had a slide where you had a vocabulary of base qualifiers, such as 0 less than equal to me.
Oh, that's right. Yeah.
Now, you could also infer the qualifiers by looking at the program, taking the branch conditions.
Yeah, we don't do that yet.
You don't do that?
No. We do not no inference of that kind at all.
That under Q1, if I see 0, then that means your program did not use any type qualifiers at all?
No. It means that all the qualifiers were scraped from the specification. So if the sortedness specification uses a qualifier v greater than 0, uses a predicate v greater than 0, then those we'll use always. We don't look at the program, but we just scrape the ones from the spec.
How many qualifiers are there in your base library?
I wouldn't know how to answer that. So there is no base library.
On your slide.
So for example, let me describe over here. Let me tell you what Q1 means over here. Okay, so there's 2 tables, right? For the array bounds, we used a base library that included the inequalities qualifiers, those 4 or 3, I forget what it was.
So that's on your slide, that's what your base library is?
For the array bounds.
Okay.
For these, the base library is, the base library is actually nothing. We just use it with the qualifier scraped from the spec. So in both cases, we're just using qualifiers that are scraped from the spec. The specification says, okay, so if the type specification says mumble, then we just scrape those. We don't actually look at the program yet. Okay, and so these actually need the balanced ones need extra qualifiers for difference and height and various things. Some are quite complicated, to be honest. Yeah.
And your qualifier has, let's say, 1 star.
Yeah.
Then your algorithm actually increases by n.
Yeah, so those stars can get instantiated crazily, right? The thing that saves us, though, is the scoping constraints. Because not everything is actually in scope at that point. A, the scope, and B, the type. So you can have a whole bunch of variables, but if the star says, there's a less than next to the star, I can only instantiate with integers.
Your algorithm itself, inference algorithm itself is linear. It's not like exponential in the number of qualifiers.
It's not linear, it's not exponential either, it's somewhere in the middle. It's actually quadratic, because what you do is, you see I showed you that you only make one pass over the constraints, but the fixed point, you may have to make several passes over the constraints. But if you instantiate one variable k with n, then you will only pick that guy, n times. So it's actually a quadratic thing over there.
Basically, the higher the call graph you are, the more possibilities for that star you have.
That's true. However, most of the extra stuff that's added to the environments are functions. At least in ML, one does not define a whole bunch of constant integers.
Extras that.
That's right. That's right.
Files kill you.
That's entirely possible. That's entirely possible.
Actually, I had I don't know. Maybe we should take this offline, but I'm rather confused why this approach that essentially exhaustively looks at the qualifiers and eliminates them one by one is superior to just essentially doing a bottom-up pass with whatever constraints you have, iterating over strongly connected components the way you do just straight from the book essentially, and getting the same result. I mean, essentially, instead of starting with everything and eliminating things that don't work, you start with nothing and grow it up. Why do this?
The short answer is it's easier to explain. In fact, the constraint solver doesn't pick the constraints in some random order. It actually uses strongly connected components, and it picks a dependency. We do, however, start with there's a technical reason for why we start with all the qualifiers and then whittle away, which is that's the only way you get to the least fixed point.
That's right.
If you start with everything, then you can end up with multiple fixed points. But if you start this way, you're guaranteed to hit the least fixed point. But we can take this offline. Shaz is jumping on his seat.
Just add this.
Yeah.
This fixed point business was all invented. It's already published in 2 papers by the Houdini. This was basically the Houdini algorithm. They proved the fixed point theorem.
Yeah. Fair enough. And actually, I mean, this is like Ed Clark, 1978, Shaz.
Oh, that I don't know.
I mean, the point here is not the fixed point algorithm. Fixed point algorithm is like an off-the-shelf tool at this point. But the thing that you start, I'm serious, is that you work your way up. No, I mean, really, it is. I mean, this is really old, that you start with the empty thing. I'm not being facetious.
Well, right, I mean, that's just out of the book.
These are just very standard. You start at the bottom, but that's why we start with everything. Everything is actually the bottom, is the lowest thing, and then you work your way. Because of conjunction.
I don't know. We'll take it offline.
Yeah.
Once you're finished with this,
I'm almost done. Recursive. There's a gushing email from the author who says, "Wow, I can't believe you found this bug. It took us a great deal of sweat to figure out the invariants. They are pretty hairy, and it did take us a great deal of sweat too." But okay, so that's pretty much it. There's a bunch of things that remain to be done. One is that the error messages are, with types it's already bad enough. With model checking, you get a complete path. This is bad for various reasons, but one of the good things is you get a good counterexample. With types, you don't really get a counterexample. And so one of the interesting things would be to try to figure out how to make this more usable by providing more interesting error messages instead of type check fails on line 22. Mutable state is the other big thing. And finally, of course, is there's heuristics for figuring out these qualifiers. So if you've learned nothing else, the point of this is not the least fixed point algorithm, which we all learned a long time ago. The point is that really, model checking, abstraction, abstract interpretation, etc., they're great for path and value information. But types tend to be very good at reasoning about these complex structures like higher order code, recursive data types, etc. And if you put them together, they really mix rather well. And you get very precise verification. And that's it. There's an online demo, papers, etc. But now I'll take questions. Yeah, Chris.
And all of the different sorting algorithms, the fact that it inferred the list for sort is pretty amazing. So I'm wondering, so Haskell has this one-line demo of quicksort where you use the built-in partition function in Haskell and the built-in concatenation function in Haskell. Can you handle that, or do you actually need to expand
we actually have to cheat a little bit for quicksort, and I'll tell you why. I can actually show you the code, but no, I can't. The trick is, and the problem is, in fact, exactly in the partition function, because, check it out, the way partition works is that it takes as input a function which is of type alpha to bool, right? And then it returns, an alpha list, and it returns as output a pair of alpha lists. times alpha list. Okay. Now, if you think about it, there's no way I can, I don't allow these functions to appear in my predicates because I would have this weird, maybe we can, but we just don't want to tax yikes too much. Is that what I would want to say is that this is a list of values, all of which, it's a list of values v such that f of v is true, and this is a list of values such that f of v is false, right? And now we're reasoning about these higher order functions inside the theorem prover. Maybe this can be done, but as I said, we don't want to do it. So we cheat a little bit. What we do is we change the partition function. So we create a new type. We call it, we call it alpha beta booleans. Okay, which is basically it's either a true of alpha or a false of beta. Okay, what's that? Type state. There's no state anywhere. We encoded the value. I like to think of it as the value. There's no state. Okay, and now so we've encoded the value inside the type, and so now what partition does is I give it a function that takes oh my god, I have to make something else up, C, and it returns an alpha beta boolean, and then I give it a C list. And it returns an alpha list times a beta list. Okay, so now where the function earlier, when it would return true, it returns the same thing, but with the true constructor. And when it would return a false, it would return a false with the same, it would return the same value or with the same constructor. So, okay, and now with this, it's just the same. If you use this flipped out partition, then it's the same quicksort. Yeah, because so then it figures out that we can talk about this offline. Yeah.
Okay, so the first part of the talk, which is about these the normal types and doing that, I find, and as you said, it's the same, similar to model checking using some kind of predicates.
Yeah.
You have some stars and some mild. But the second part, I think, where you have all these other things, the higher order functions, it's difficult to translate that to the imperative language world, right? But I'm just wondering whether for the recursive data types, there is a lesson to be learned even for the imperative world. Namely that if I had, and it's about data structures usually being recursive and so on, right? Maybe the properties of them are also recursively provable and therefore maybe recursive types are good. Is that maybe one can have recursive types for the data structures, but use it even in an imperative programming language, where you use the same thing, but as you assume that the class which manages the data structure is typed with these types, and so is that something which is which will translate to the...
I think, I'm betting it will, but I think, by the way, the higher order function thing also will. Higher order functions actually appear in a lot of places, even in imperative code.
But you clean that out.
A method is kind of, if I pass an object around, it has a method. That's sort of like a higher order function. You're right about the recursive types. It's really what's going on is that the type system is giving us a strategy for doing this quantifier, generalizing, and instantiation. So every time I construct a list using a cons of head and tail, that's really is doing a generalization at that point. You say, oh, you're doing a cons, what do I know about head, what do I know about tail, let me do a generalize at this point. And every time I do a pattern match, I say, oh, here's a list, let me rip it out into, it's doing an instantiation. Okay, under the hood, that's really what's going on. And so really this combination of the types and whatnot, the types are really is basically a heuristic, if you will, for quantifier generalization and instantiation.
And the only other thing which we have is separation logic, kind of constructs for reasoning about the heap, right?
Yeah.
And maybe these two can combine as well. Is that this recursive type seems to be a nice way of specifying something about it.
Yeah, it's that's the hope. What's that?
There's a Havoc too also, by the way.
I was going to say actually this. There is the style we write the sorted thing is actually, to me, I don't know what it is, but viscerally it feels to me very similar to the way Shaz and Shuvendu write it in their, what do you call it, LisBQ, where you say, but somehow it feels, I'll tell you why it feels the same. At no point do you say anything about the next element. The most natural way to write a sorted list is you say, I am less than the next guy, and this is true everywhere. While here you don't. You just say, I'm less than everybody else after me. And they also say something like, for everybody in this list, if you start at that point, for everybody after them, they are less than. But I don't know if there's any deeper connection. There's just this kind of...
The quintessential example of a kind of non-recursive kind of thing is a grid, right? If you have a two-dimensional array or a grid or whatever, it would be really hard to do these things.
Any kind of sharing. I mean, this way, the nice thing is you have exactly one direction to propagate the invariance down. But if there's some kind of confluence, who knows what's going to happen?
Unbounded.
And it's unbounded. There's another hand somewhere, but...
This speaker. Right?
What's it? This speaker.